In this first model, we are going to talk a little about some basic concepts related to nature-based solutions and water security. The idea is to be able to have a common understanding about some terms and some elements that we will be using during the course. In this presentation, we will see some basic concepts and principles of analysis in watersheds. We will see that watersheds are really our basic units of analysis, and that being able to understand watersheds is really important in all our analyses. We will also see some definitions of ecosystem services and types of ecosystem services. Then we will review the concept of water security, the dimensions of water security, and some challenges. We will move forward to review in a more formal way the definition of nature-based solutions and the opportunities of nature-based solutions in water security. We will see a simple analytical framework to be able to connect nature-based solutions with ecosystem services and water security. And finally, we will see some recommendations for the analyses. Okay, we'll start with some basic concepts and analysis principles for watersheds. When we look for a formal definition of watershed, we will probably find this definition. A watershed is any surface area from which runoff resulting from rainfall is collected and drained through a common point. And this is correct. In fact, this is the definition. A watershed is an area, and it is an area where all the drops of water that fall in that area drain to the same point. And with this definition, some concepts appear, and that is that this watershed must have a boundary. And this boundary divides if a drop of water drains to one area or another. And of course, the other concept is our common drainage point, which is very important because it defines the extension of the watershed. But this formal definition contains much more information than we can see initially. And it has a very powerful concept, which is that the area in which all the water drains to the same point implies that a watershed is the area in which we are all connected by water. And perhaps thinking about this idea also generates a whole concept of analysis, because analyzing connected systems requires special approaches. And recognizing that in this area we are all connected also implies different responsibilities, and it is that since we are all connected, what each one of us does in this area will affect the others, precisely because we are connected. So, in this concept of connection, a basic principle of basin analysis appears, and it is the upstream-downstream relationships. Traditionally, in water systems, three zones known as source zone, transition zone, and floodplain zone are identified, and this classification of zones comes from geomorphological analyses for rivers, and to indicate some processes in terms of production and transport dynamics of sediments. But it also allows us to see a little what the changes in the water systems mean. For example, the floodplain zone, where perhaps the greatest diversity of river geomorphological units is found, depends entirely on the dynamics and balance in the source zone and in the transition zone. The alternations in these zones directly affect the conditions in the floodplain zone because they are connected elements. But there are also ecological processes that are affected in the transition zone or source zone if impacts are generated in the floodplain zone. For example, fish migration. If for some reason migration is impacted in the floodplain zone, for example if we build a barrier, a dam, it cuts off the dynamics of fish communication from downstream to upstream, and this also generates impacts in the dynamics of the upstream zones. What we are trying to say is that water systems are complex, and the upstream-downstream relationships are also very complicated and require a significant effort to be able to understand them correctly and are very particular to each basin. But another complexity in the principles of analysis of water systems is related to the fact that they are multiscalar systems. And this is very interesting when doing analysis, but it's also very challenging. In these cases, the temporal and spatial scales are related, and a good understanding of the water system implies understanding these multiple scales. We have scales that include ecoregion, catchment, landscape units, reach scale, geomorphic unit, hydraulic unit, and structural elements. And such an approach in which these scales are understood to be related is known as nested hierarchy to conceptualize spatial cross-scalar relationships. It is really very important to understand that the understanding of a water system includes the understanding of its multiple scales and their relationships. These analyses are not easy, but they are necessary. To know the water system is to know it in its multiple scales. This is really very important. So, all this to explain that our basic units of analysis are really the watersheds. When we do hydrological and benefit analyses in the implementation of nature-based solutions, we use the basin as the modeling and analysis unit. It is our basic unit. Okay. To understand the water system, there are several key questions that we must answer. This approach is based on the principles of the River Styles Technical Framework, developed by Professors Gary Brearley and Kirsty Friars. When the water system is described, answers are given to the questions of, what does it look like? And how does it behave? These are basic questions for the description of the water system. When the system is explained, we concentrate on the questions of, why does it look the way it does? And what controls system behavior? And finally, when we can describe the system and explain it, we can now try to predict it, and this is related to questions like, what is the system going to look like in the future? And if we change X or Y, how is the system likely to respond? This may sound simple, but it really isn't. Being able to describe the system is an effort that implies knowing the basin very well, working in the field, seeing the river during dry seasons or during high flows. It's an extensive effort. Explaining the system is also complex because you have to go beyond what can be seen in an obvious way and build relationships, especially these relationships of upstream and downstream systems, in order to identify what controls the appearance of the system. And well, predicting is always difficult. Trying to go to the future always sets challenges because of the uncertainty we have about some things. However, prediction is fundamental in the work we do in basins and in water systems. What we always want is to be able to know what would happen if we did something different. The actions we do how can change the response of the system. The prediction component in water systems is very important, and we can see possible futures under different criteria. Usually, we are interested in how the future could be if things continue the trend that has been seen in recent times. We call this a business as usual scenario. But also, in our particular case, we want to know what the response would be like in a scenario where we implement, for example, nature-based solutions, or if we carry out conservation activities in the basin. And in this way, we can build other scenarios in which we do different activities or changes. And then, we establish a key concept in prediction analysis, which is the concept of scenario, as a set of conditions that could occur in the study area and for which we want to predict a response. Here is a key question in prediction, and it is, how to predict with an acceptable uncertainty. This question is not easy, but there are technical frameworks that allow us to approach this problem in a way that we obtain acceptable answers. We are going to see that using a modeling protocol, for example, helps to have better answers. When we enter the world of predictions, we want to answer the question of, what are the changes in the water system with different future scenarios? And the reality is that a basin can have many changes. Some areas are transformed into cities. In others, the land cover changes. In other places, infrastructure projects are developed. Agricultural developments. I mean that there are many changes in the system, and that we want to have a tool that allows us to make the prediction. One of the tools that allows us to make predictions is mathematical models. Models are simplified representations of reality, and simplified is highlighted on the slide because we must not forget that mathematical models are not reality itself. They are a representation where we have made many simplifications, because reality is very complex. But we believe that these simplifications and representation allow us to obtain an adequate response to the questions we want to prediction. On the slide you can find a classic representation widely used in hydrology, which is to represent the basins and the water system using tanks. Of course, the reality is not that we have tanks. This is just a conceptual model that makes it easier for us to represent. We like tanks because they have control volumes. They allow us to connect inputs and outputs, and they are generally simple. So, using tanks helps us simplify reality. This is just one example of a tank-based model build, but of course there are different types of conceptual models. In mathematical modeling, we always have this key question, which is how to have a mathematical model that allows an adequate prediction. And something that helps us to carry out an adequate mathematical modeling process is to follow a modeling protocol. This is a standard modeling protocol that is reported in the literature and has several steps for the modeling exercise. Following these steps helps us to have a predictive mathematical model and also to recognize the capabilities and limitations of our model. This modeling process starts with define modeling goals and objectives, preliminary research, formulate the mathematical model, select or develop the mathematical model, model construction in the specific application, calibration, validation, scenario formulation and simulation, analysis of results, and post-audit. Following this type of protocol helps us to have a clear mathematical modeling process and better tools. I would like to highlight that a rigorous mathematical modeling exercise is required to have a predictive model that allows connecting the interventions in the watersheds with the ecosystem services and benefits in water security.